Hello friend, welcome to this lecture. In this lecture we will continue our study of finding the n linearly independent solution of x dash equal to Ax, where A is n cross n matrix. And in previous class we have seen some example where we have n distinct eigen values of the coefficient matrix A, and there we have find out n linearly independent eigenvectors, and hence we can write down the general solution in the form of n linearly independent solution. And we have seen that in the case when we do not have distinct eigenvalues, then we may or may not get n linearly independent eigenvectors, and hence we may not get n linearly independent solution of the form of e to power lambda t into vector v. So we generalize, then we try to generalize, we try to get the motivation from the scalar case, that the in a scalar case of solving x dash equal to Ax, let me write it here, that x dash equal to Ax, our solution is coming out to be xt equal to e to power at into some constant c. So we have done in the first case that we in place of this constant we have written that e to power at, and let us say v is n cross 1, and we have seen that this will work very nice if A coefficient matrix A has n distinct eigenvalues. So for in n distinct eigenvalues, this candidate works very fine and it will give you solutions, n linearly independent solution. But in case when A has repeated eigenvalues, then this may not work good, and then we thought to generalize this candidate, that is candidate here, and we thought that is it possible to find out a formula for e to power at and v as n cross 1, and we have seen in previous class that this will work as a solution. In fact, we have shown that x dash t equal to a e to power at into v, and this implies that this is a x. So x dash t will be a of x for any constant vector v here. So but e to power at, we have shown that it is nothing but a power series, then it is at n upon factorial n is from 0 to infinity. So in this sense we simply say that this is an infinite series in the powers of matrix A, and it is quite difficult to find out the sum of the matrix sum of this infinite series. Then we will focus our attention on this vector v, such that this infinite series will be say truncated into finally many terms. That is what we want to discuss in this lecture. So what we have done in previous class, that in the case when we have say k number of linearly independent eigenvector which is strictly less than n, then we have to look at the solution of the form e to power at v, and with the help of this we try to find out the remaining n minus k linearly independent solution, and we define e to power at as a limit of this infinite series, and we have shown that this series is converged uniformly for all t, and norm of e to power at is less than or equal to e of norm of at for each fixed but arbitrary t, and we have shown that that d by dt of e to power at is equal to a e to power at, which shows that this is actually e to power at v is actually a solution for every constant vector v here. And to find out, to simplify this e to power at, because using the infinite series formulation of e to power at is quite difficult to calculate. So we look at this observation that e to power at v can be written as e to power a minus lambda I t into e to power lambda I t into v. So here this we are able to do because these two matrices commute. So here we have shown that here we have observed that e to power a plus b equal to e to power a into e to power b, or e to power b into e to power a, when this a and b are two commutative matrices. So it means that if a b equal to b a, then I can write this. In general it may not be true for arbitrary matrix A and B. So, here since A minus lambda I and lambda I commute, then I can write e to power a t v as e to power a minus lambda I t into e to power lambda I t v, and also we have shown that e to power lambda I t v is nothing but e to power lambda t v. So, it means that e to power a t v is equal to e to power lambda t into e to power a minus lambda I t into v. So, now we will focus on this and we try to find out the vector v such that this matrix in fact e to power a minus lambda I t into v is basically I plus a minus lambda I t plus so on a minus lambda I n t to power n upon factorial n and so on into v, right. So, we will focus, we will find v such that this infinite series can be truncated into a finite terms. So, our strategy will be like this, that while finding the general solution of 1, that is x dash equal to a of x, or equally finding n linearly independent solution of 1. In fact, if we are able to find out n linearly independent solution of 1, then we can write down the general solution as well. Then we have the following two possibility. One possibility is that A has n linearly independent eigenvectors, and hence we can write down n linearly independent solution of the form e to power lambda t v. And in the second case, if A has less than n linearly independent eigenvectors, then A has only k linearly independent eigenvectors, then we have only k linearly independent eigensolution of the form e to power lambda t v. This may happen when eigenvalues are not distinct. So, it means that here the case is corresponding to the case when eigenvalues are repeated eigenvalues. So, we now focus on this case too. So, here we may recall a result of linear algebra that says that the linearly independent the number of linearly independent eigenvectors correspond which we call as geometric multiplicity cannot exceed the number of repetition of the corresponding eigenvalue, that is commonly known as algebraic multiplicity, that is AM is greater than or equal to GM. Let us try to understand this, that we have a matrix A, then we have some eigenvalue lambda, suppose it is repeated say k times. So, suppose it is lambda is the root which is repeated k times, then we call the algebraic multiplicity of lambda I is k. So, algebraic multiplicity of lambda I is given as k, the number of repetition of these roots is your algebraic multiplicity. Now, corresponding to lambda I, just find out your number of linearly independent eigenvectors, and the number of linearly independent eigenvectors corresponding to lambda I is known as geometric multiplicity of lambda I. So, lambda I, so geometric multiplicity is what? The number of linearly independent eigenvectors corresponding to this lambda I, and that we call as G of M, geometric multiplicity. Now, if geometric multiplicity is equal to algebraic multiplicity, then for each lambda I, then we have n linearly independent eigenvectors. But we have shown that in the case when algebraic multiplicity is strictly greater than geometric multiplicity, and the result says that this algebraic multiplicity is greater than or equal to geometric multiplicity. In fact, if you remember this matrix 1 1 0 1 0 1 1 0 0 1, here you have shown that algebraic multiplicity of 1 lambda 1 equal to 1 is 3, but geometric multiplicity corresponding to lambda 1 equal to 1 is only 1. So, here algebraic multiplicity is 3 and geometric multiplicity is 1. Here we have seen that there is only one linearly independent solution is available, that is I think 0 0 1, that we can verify again. So, here we have only one linearly independent solution. So, geometric multiplicity is 1, algebraic multiplicity is 3. So, here this is the result of linear algebra, this you can find out in any standard textbook of linear algebra. Then so it means that we are in trouble when we have the case that AM is strictly greater than GM. So, to find remaining n minus k solutions, we consider only those eigenvalues of A for which Am is strictly greater than Gm. So, let us say that let us have lambda is such an eigenvalue of A and find all vectors V for which A minus lambda I V is not equal to 0. It means that V is not an eigenvector of A corresponding to lambda, but A minus lambda I whole square into V equal to 0. So, it means that it is not an eigenvector, but that it is a kind of a solution of A minus lambda I square x equal to 0. So, for each this kind of vector V, which is commonly known as generalized eigenvector, we can write down the expression for e to power a t v as e to power lambda t into e to power a minus lambda I t into v. This we have already shown. Now, focus on this e to power a minus lambda I t. So, this e to power lambda t I have written as it is. Now, this is what? This is written as let me write it here. It is what? E to power a minus lambda I t v. So, it is I plus a minus lambda I t plus a minus lambda I square t square upon factorial 2 and so on, right. Then if we write it this as that is V plus a minus lambda I t v plus a minus lambda I whole square t square factorial 2 v and so on. So, if so it is basically e to power lambda t. So, if it is e to power lambda t v, right. So, here if you look at, if this is non-zero, then we make that this term is 0, and if we make this term as 0, so remaining term will also be simply tend to 0, simply goes to 0. So, it means that this infinite series is now reduced to only first two term. So, that is what is the idea here, that here we simply find out e to power a minus lambda I t, that is I into v plus a minus lambda I t into v, and since a minus lambda I square v equal to 0, then we can verify that a minus lambda I cube into v is also 0. In fact, this can be written as a minus lambda I into a minus lambda I whole square v. Now, this is 0. So, a minus lambda I applied on 0 is gives you 0, and hence we can say that the higher powers of a minus lambda I 3, 4 and operating on v will give you value 0. So, it means that this infinite series is now reduced to only two term, that is v plus t a minus lambda I v equal to 0. Now, if you say that if v is such that a minus lambda I v is equal to 0, then it will reduce to only one term, that is e to power lambda t into v, and that will shows that e to power a t v is nothing but e to power lambda t v, and in that case v is known as eigenvector of A corresponding to the eigenvalue lambda. So, here we have shown that if v is an eigenvector, then it is reduces to e to power lambda t into v. If v is not an eigenvector and we call as a generalized eigenvector, then it will contain at least one more term to e to power lambda t into v. So, here what we have shown that if we choose v in a way in this way, then e to power a t v can be written as e to power lambda t v plus t a minus lambda I v, and this will work as an additional solution of 1, and we do this for all such eigenvalue lambda of A for which Am is strictly greater than Gm, and the idea is to find out the remaining Am minus Gm number of solutions. And if we have enough number of solution by the previous step, then we stop and we will write the general solution in terms of a linearly independent solution. But if we do not have enough number of solution, then we find out all vectors v for which this a minus lambda I square v is non-zero, but the next higher power, that is a minus lambda I cube v is equal to 0, and in this case your e to the power a t v will contain one more term, that is t square upon factorial to a minus lambda I whole square v. So, if this term is if this term is 0, then it will reduce up to only these two terms, but if this term is non-zero and next term is higher term is 0, then we have one additional term. Okay. So, e to the power a t v is now reduced to e to the power lambda t v plus t times a minus lambda I v plus t square upon factorial to a minus lambda I square v, and we call this as an additional solution of 1, and we keep on repeating this until we get n linearly independent solution. That is, for eigenvalues which have am is greater than gm, we have additional am minus gm number of solution obtained by the given method. So, this is the criteria. What is let me summarize this. You have a matrix A, there we have some eigenvalues, say lambda 1 to lambda k, and suppose there exists some lambda I for which your am is greater than gm. Then for this lambda I you perform the given step and you find out the generalized eigenvectors. In fact, this vector is also known as generalized eigenvectors, and you find out generalized eigenvectors till that we have the am number of solutions available. We already have am minus we already have gm number of solution, then remaining am minus gm number of solution we can obtain by the given method. It means that we need to find out generalized eigenvector am minus gm number of generalized eigenvector. Now, the guarantee that this method will work is given by the following lemma, which we assume without any proof, and this basically related to finding the Jordan canonical form of a given matrix. Now, what this lemma says, let us try to understand. Let the characteristic polynomial of A have k distinct roots, that is lambda 1 to lambda k, with multiplicity n1 to nk respectively. So, it means that the algebraic multiplicity of lambda 1 is n1, algebraic multiplicity of lambda 2 is n2, and so on. Suppose that A has only Vj that is less than nj linearly independent eigenvectors with eigenvalue lambda j. So, here algebraic multiplicity is nj, but geometric multiplicity is only Vj. Then the equation A minus lambda j I whole square V equal to 0 has at least one more independent solutions. So, it means that if we are having only say Vj number of linearly independent eigenvectors where Vj is strictly less than nj, then the equation A minus lambda j I whole square V equal to 0 has at least one new independent solution, that is Vj plus one independent solution. Earlier we have only Vj independent solution, now we have one, that is Vj plus one independent solution of A minus lambda j I whole square V equal to 0. So, more generally, if the equation A minus lambda j I m V equal to 0 has only mj, which is strictly less than nj independent solution, then the equation A minus lambda j I to power m plus 1 V equal to 0 has at least mj plus 1 independent solution. So, it means that here this system will have mj plus 1 independent solution, out of which you can say that mj is already obtained. Okay. So, we will choose one new solution which is linearly independent solution to the previous one. So, this lemma is the guarantee that the above what we have defined will going to work. Okay. So, now let us take one example based on this procedure. So, example 1, that find the solution of the following initial value problem, x dash equal to 2 1 3 0 2 minus 1 0 0 2 x, and initial condition is given as at t equal to 0, that is 1 2 1. So, here first thing we need to find out, since we need to find out the initial value problem. So, we need to look at the general solution and then we have to find out the values of constant with the help of initial condition. So, first we find out the 3 linearly independent solution. So, for that we need to look at the eigenvalues. So, if you look at the eigenvalues, since it is upper triangular matrix, so eigenvalues are nothing but the diagonal entries, and if you look at diagonal entries are 2 2 2. So, here eigenvalues are 2 with algebraic multiplicity 3. So, eigenvalues of this matrix is 2 with algebraic multiplicity 3. Now, look at the eigenvector. So, to find out an eigenvector, let us find out the solution of A minus 2 I V equal to 0. So, we simply say that we solve this A minus 2 I V equal to 0, and when you solve this, we will get that V 2 and V 3 is equal to 0. In fact, we can solve this, and it is V 2 plus 3 V 3 is equal to 0 and V 3 equal to 0. So, V 3 is equal to 0 implies that V 2 is equal to. So, we have only one arbitrary value, that is V 1. So, here V 1 may take arbitrary value, and we can write down that V 1 may be 1 0 0, and one solution we can obtain of the form of e to power lambda t v, that is given as x 1 t equal to e to power 2 1 0 0. So, by the previous method we have only one solution of the form e to power lambda t v. So, we need to find out the remaining two linearly independent solution. For that we have to find out the generalized eigenvector. So, look as so here in this example, A has only one linearly independent eigenvector for repeated eigenvalue, that is lambda equal to 2. So, algebraic multiplicity is 3 and geometric multiplicity is 1. So, AM is strictly greater than GM. So, one thing we observe like this, that AM is greater than GM for this example. So, here we need to find out the discussed method to find out the remaining 3 minus 1, that is 2 linearly independent solutions. So, for that look at the solution of A minus 2 I square u equal to 0. So, if A minus 2 I u equal to 0 has say one solution, then A minus 2 I whole square u must have two solution at least. So, just calculate A minus 2 I whole square, and it is coming out to be 0 0 minus 1 0 0 0 0 0 0 and u 1 u 2 u 3. Here I am taking the liberty that A minus 2 I square is calculated in this way, you please calculate. So, when you look at, then u 3 is equal to 0. So, here u 1 and u 2 are arbitrary. So, their possibility are like 1 0 0 and 0 1 0, right. So, here we have two linearly independent eigen solution of A minus 2 I square u equal to 0, and here we choose a value which is not which is independent to your previous eigenvector, because here we have to put one more condition that A minus 2 I u is non-zero, right. So, it means that the earlier eigenvector, that is 1 0 0, if we take, then A minus 2 I u has to be 0. So, we drop this and write down our solution as 0 1 0. So, here we take the vector u as 0 1 0, so that A minus 2 I u is not equal to 0, and of course, that is linearly independent eigenvector, and it satisfy A minus 2 I square u equal to 0, and hence with the help of this u, now solution, second solution x to t is written as e to power a t 0 1 0. Now, e to power a t has this expression e to power 2 t e to power a minus 2 I t 0 1 0. Now, a minus 2 I is basically what? This is I plus a minus 2 I t plus a minus 2 I square upon factorial to t square and so on. When you operate on v, then this will give you v and this will give you some value, and these term onward it is 0. So, it will have only few term, that is identity means 1 0 0 0 0 0 1 0 0 0 1 plus t times a minus 2 I t is basically what you have already calculated. So, a minus 2 I is 0 1 3 0 0 minus 1. So, 0 1 3 0 0 minus 1 0 0 0 and yeah, and this into v, and when you simplify, what you will get? You will get here the value e to the power 2 t 1 0. So, here this I is basically 1 0 0 0 1 0 0 0 1 plus t times 0 1 3 0 0 minus 1 0 0 0 into v and into e to the power 2 t. Now, let us calculate this. For this let us write it e to the power 2 t, and this is I plus t times a minus 2 I into 0 1 0. When you simplify, it is written as e to the power 2 t as it is. This is written as 1 t 3 t 0 1 minus t 0 0 1 and operating on 0 1 0. When you solve this, then you will get e to the power 2 t into t 1 0, and that is what we have written as the second solution x 2 t as e to the power 2 t t 1 0, and this is linearly independent solution of x dash equal to Ax. So, how you can check this, and this is a linearly independent solution that you can easily check at point t equal to 0. If you look at the first solution will be what, e to the power 2 t 1 0 0, and it is e to the power 2 t t 1 0. If you put t equal to 0, you can see that x 1 0 and x 2 0 are linearly independent. What is x 1 0 here? X 1 0 is basically 1 0 0 and x 2 0 is basically, so x 2 0 is basically is coming out to be 0 1 0, and you can see that these two are linearly independent. So, x 2 t and x 1 t are also linearly independent. Now, but still we have only two solution, because by the previous method we are having only one new solution we have obtained. So, but we need only two linearly independent solutions. So, we perform one more iteration of the method and find all the three solution of 3. So, look at a minus 2 I cube into w equal to 0. Now, a minus 2 I cube is basically nothing but a 0 matrix into w1 w2 w3 equal to 0. So, here you can simply say that this will have one more solution of the previous method, that is in previous method we previous step we have two solution. So, here we will have three solutions. So, here we have solutions, we can have 1 0 0, 0 1 0 and 0 0 1, and since we need to look at that a minus 2 I w is non-zero and a minus 2 I square w is non-zero. So, we have to leave these two option. So, here we take the solution as w as 0 0 1, so that a minus 2 I cube w is 0, but a minus 2 I square w is non-zero and a minus 2 I w is also non-zero. So, here we take w as 0 0 1, and corresponding to w, now solution is what? Solution is given as x 3 t equal to e to the power 2 t into e to the power a minus 2 I t into 0 0 1, and if you expand this e to the power a minus 2 I t, then it is nothing but I plus t a minus 2 I plus t square on factorial to a minus 2 I square operating on 0 0 1, and when you simplify, I am not simplifying here, I am just say observing that if you simplify, you will get e to the power 2 t 3 t minus 1 by 2 t square minus t and 1. So, this will be your third solution corresponding to lambda equal to 2. So, now we have obtained three linearly independent solution corresponding to lambda equal to 2. So, we stop our method and we can write down the general solution as C1 x1 t plus C2 x2 t plus C3 x3 t, where x1 t is the form of e to the power lambda t into v, and x2 and x3 t are solution obtained with the help of generalized eigenvector. And here we can check that these are linearly independent solution. For that, you simply put t equal to 0 and calculate x1 0, x2 0 and x3 0, and you can see that these are linearly independent eigenvectors. We can write that xit are linearly independent solution of equation 9 and given by the equation 4, 5 and 6 respectively, and using initial condition we can fix our constant C1 and C2 and C3, and in this case our solution is constants are coming out to be 1, 2 and 3. In fact, we can write it solution as follows, say, so x of t equal to C1, now e to the power 2 t you can take it out, and this 1 0 0 plus C2 e to the power 2t, and here it is T10 plus C2 C3 e to the power 2t, and here solution is basically 3t minus half t square, 3t minus half t square, and 2 minus t, it is minus t and 1. So, initial condition is given as what? Initial condition, let me look at initial condition is 1 to 1. So, x of 0 is 1 to 1. So, when you put t equal to 0, what you will get? 1 to 1 equal to C1 1 0 0 plus C2 0 1 0 plus C3 0 0 1, and you can easily check that C1 is coming out to be 1, C2 is coming out to be 2, and C3 is coming out to 1. So, putting the C1, C2, C3 values in the general solution, you can write down the solution of the initial value problem as e to the power 2t and 1 plus 5t minus half t square, 2 minus t and 1. So, this is the solution of the initial value problem 3. So, here by this example we have shown that in case of repeated eigenvalue, how to find out the n linearly independent solutions here. Now, we move to the concept fundamental matrix solution. So, once we have n linearly independent solutions, then we can write down the general solution, and we can write down the general solution as this: x of t as linear combination of xit, where xit are linearly independent solutions of the equation x dash equal to atx. Then when we have n linearly independent solutions, say x1t to xnt, we commonly call these linearly independent solution as a fundamental set of solutions. Now, here we may have different choices of n linearly independent solution of equation 9. So, we may have different fundamental set of solutions. So, a fundamental set of solution basically gives you a set of n linearly independent solution of x dash equal to atx, and once we have fundamental set of solutions, then you can write down the general solution in the form of fundamental set of solution, and it is given as xt into c, where xt is basically what? Xt can be considered as a matrix whose columns are your n linearly independent solutions of x dash equal to atx, and c is a column vector c1 to cn. So, it means that your any solution x of t, so x of t is given as x of t into c, where x of t is basically n cross n matrix and c is n cross 1, where xt is a matrix whose columns are x1t, x2t and so on. So, it means that with the help of these n linearly independent solution, we form a matrix which we call as a matrix solution, and with the help of matrix solution we can write down the general solution as this xt equal to xt into c. So, we have a new definition. We say that a matrix of n rows whose columns are solutions of equation x dash equal to atx is called a solution matrix. So, this xt is a solution matrix because columns of this matrix forms a columns of this matrix is basically solutions of x dash equal to atx. Then we define fundamental matrix solution. The only difference between matrix solution and fundamental matrix solution is that the columns are now linearly independent solutions of x dash equal to ax. So, it means that a matrix xt is called a fundamental matrix solution of 9 on I if its columns form a set of n linearly independent solutions of x dash equal to atx. So, it means that if columns forms a fundamental set of solutions, then this matrix is a fundamental matrix solution. Is it okay? So, now let us consider the example. Here in this example, we need to find out a fundamental matrix solution of the system of differential equation x dash equal to 1 minus 1 4 3 2 minus 1 2 1 minus 1 into x. So, here first thing we need to observe that what are the eigenvalues of this matrix. So, here I am leaving it to you to see that the eigenvalues are given as 1, 3 and minus 2, and please observe that these are all distinct. So, it means that the corresponding eigenvectors are also linearly independent, and we can find out like V 1 as -141, V 2 as 121 and V 3 as -111 as linearly independent eigenvectors corresponding to 1, 3 and -2. So, here we can find out 3 linearly independent solutions as e to the power t into -141, e to the power 3t into 121 and e to the power -2t -111. So, it means that here this is your x1t and this is x2t and this is your x3t. So, once you have x1, x2, x3t and these are all linearly independent. So, the matrix having this x1t, x2t and x3t as columns is not only a matrix solution, but it is also a fundamental matrix solution, because these 3 are linearly independent solutions. So, here this x t is equal to minus e to the power t, e to the power 3 t minus e to the power -2 t, 4 e to the power t, 2 e to the power 3 t, e to the power -2 t, e to the power t, e to the power 3 t, e to the power -2 t is a fundamental matrix solution of the equation x dash equal to a x, where a is given by 1 minus 1 4 3 2 minus 1 2 1 minus 1. So, here we obtain the fundamental matrix solution like this. So, with this we stop discussion of for this lecture. We will continue discussion of about the fundamental matrix solution in the next class. Thank you very much for listening us. Thank you.